You know, why do we care about stress? So, in essence, well, if you can think about, this problem here, if you've got, I told you that, for a given stress, we can look at the ratio of our applied load to our area, and we can work out a stress. A lot of physical materials have, some limit to them, some stress limit before they break. So we can utilize that in order to determine sort of what external force an element can support. And so that's really the basis of design. So let's work with a small example here. So for our example, we're going to have two elements. Again, we'll stick with a square here. And this time we're going to put them into tension. So this is a square which is 10 millimeters by 10 millimeters. So A equals 100 millimeters squared. And we'll take another element, which is, it'll be a smaller cross section. And just assume those are the same length. Apologize with the drawing here. T and T, and this one we'll just have it be, have each of the sides be half the length of the other one. So this is a 5 millimeter by 5 millimeter. So the area equals 25 millimeters squared. So what we want to know is what load T can each of these handle. So what do we need to know there? Well, we need to know what, we need to know two things. We need to know the stress, and we need to what stress can it take in tension and what the area is. So we know the stress. Let's just assume that our stress and tension max is 300 MPa. So what we need, if we know the stress at which this material will break, which is 300 MPa, and we know the areas, we can work out, well, what forces can each of these elements hold up. And so we simply start plugging in our equation where we have our stress. In this case, instead of P, we're going to call it T over A, and that's 300 newtons per millimeter squared equals T over 100 millimeters squared. And so our allowable load to be underneath the stress is 30,000 newtons. So T equals 30 kilonewtons. And if we do the same for the other element here, so stress equals T over A, we get 300 newtons per millimeter squared equals T over 25 millimeters squared. T equals 7,500 newtons. And then we can simplify that to 7.5 kilonewtons. And, that should make sense where, if we have this area and this area, the area of this first element is 4 times the area of the other. For the same yield strain or same tensile strain that they have, well, we would expect this one to have 4 times the load capacity than the other. So that's good. So it's pretty straightforward details and calculations. So what we can then use this for is in design, if we know the stress at which a material fails, and we know what loads that we're asking it to use, well, we can work out, well, what area or what's the required section. So that might be an area, that might be a moment of inertia for bending stress. But we can determine our section geometry simply by knowing the external forces and the limit of our internal actions. And so the way we do that, there's some, I'll give you some examples of axial stress capacities for different materials. So, we'll just go. Examples. Stress. Axial stress capacity. So these are some common materials which are used in structures. So one of the most common ones, steel. Grade 300, grade 500. Well, this has an axial stress capacity of 300 MPa. And this one has a 500 MPa. It's kind of a convenient naming system which they use there. Another common material, say concrete. So in compression, it'll be between, say, typical strength between 20 and 60 MPa. In tension, somewhere between 2.5 to 4.7 MPa. And as you can see, not all materials have the same axial stress capacity in both tension and compression. So concrete's a good example of that. It's got really good compression strength capacity, but it has kind of rotten tensile capacity, which is why it's utilized with reinforcing steel in essence to be able to take that tensile load. So for timber, if we have compression parallel to the grain, it'll be somewhere between 11 to 35 MPa, and then tension parallel to grain will be somewhere between 3 to 23 MPa. And notice I said parallel to grain. So timber is what's called an anisotropic material. It has different properties in different directions. So, tension perpendicular to grain is essentially zero. It's you're pulling fibers apart. And these big ranges, so the ranges on concrete really depend upon the mix design which is in there. So the aggregate strength, how much aggregate there is relative to cement and sand and other constituent properties. With timber, because it's a natural material, you get a big range because every tree is different and unique, and different species of trees are unique and different. And so for a final one that I'll give you, say aluminium. Aluminium is really, its properties are really dependent upon the alloy which is in there. So a common one is 6061. You're going to have between 83 to 240 MPa for an axial stress capacity. And now that's a huge spread there, and that's going to be dependent upon the temper which they use, so how they harden it temper it back after hardening. So as you can see, so what as a structural engineer, what you would do is you determine your loads. You know your material, so you can figure out what your axial stress capacity is, and then you're really just trying to keep your capacity above the demand. It's really just quite that simple. So that's our sort of initial overview into stress. Well, what we want to look at now is let's start diving into the different types of stresses. And so we said briefly about direct stress or axial stress, and well, let's start there. So for axial stress, we already really have the equation for it. So we've got sigma equals P over A. But the problem with this is this equation, the simplified equation, gives us the average stress. So how do we arrive at this average stress? Well, if we want to sort of link, we took this, from a very simplified, derivation based upon statics. Well, let's look at it with just a little bit more detail and use a little bit of calculus. So don't be scared. It's a brief amount of calculus. So say, we have the same section that we looked at earlier in compression, force P, and we just look at this little tiny area, delta A, and it has this little tiny force, delta F. So really what we see is that, for the average stress, so this is P, the average stress over this small point, say we'll call it Q, average stress at Q simply equals delta F over delta A. Well, but if we want the stress at a point, really what we want to do is make this delta A smaller and smaller and smaller. And so from there, we get, stress at a point at Q equals limit of delta A approaching 0. So it's that area getting smaller and smaller and smaller down to a single point of delta F over delta A. Well, cool. Now, but if we want to find out, well, what's the stress across the whole cross section? Well, then we need to, sum all of that up essentially. And what's most convenient way to sum up large continuous areas is to use calculus and to take an integral. So if we take, integral df over A of the stress times dA, well, if we know due to equilibrium, sum of the forces in the y equals 0. So we know that P equals the integral of all of these little df. So if we take a little df over this whole section, well, and then we integrate that has to equal P for it to be in equilibrium, or else it's moving. And we're dealing with statics here. We're not dealing with movement. All right, so this one's pretty easy to wrap your head around, and this is much the same as we looked at in the beginning, where, all of these little forces add up to this force. This is essentially doing the same, saying the same thing, but just with calculus. Well, if we know that dF also equals the stress over a tiny area, well, we can say, we can equate that as well. Stress dA. And so you can think of this really as like a volume of stress has to equal this force. So you can kind of think of this bit here, as a volume of stress. And that has to equal the applied load. So I say volume of stress, and it's really a conceptual idea, and it helps with a lot of the sort of the day-to-day calculations we would do. So, I mean, if we go back to our original bit, we're really thinking about, well, if we're assuming an average stress and then it's all over, well, we're really taking the area times the height of the stress. That's a volume. And now, it's not a true volume, but it's a good conceptual idea where we think about all of this adding up to an external force. And that will be helpful, particularly when you look at things like shear stress or bending stress, and you're looking at those distributions across a section. So, and this, that's our governing equation for stress. So what we want to look at is, just do a little bit of, we showed you average stress, which, we assumed was just a uniform across the whole area. And, but what do some actual stress distributions look like? If we look at some actual stress distributions in, we'll use our little column, and again, we'll just keep this nice and slender here, and we'll put it into compression. So P and P. And what we'll do is we'll just take a series of cuts through the member and just look at what that stress distribution is going to be. And what I'm going to do is I'm just going to basically draw them out instead of deriving them. So, we take a cut at A, a cut at B, and a cut at C. And all of them will encompass, will go down on all of them. So our free body diagram at A, we have our force P, and we have our distribution. And our distribution looks something like this, where it's got this big sort of sloping curve to it. Well, but then if we go our free body diagram at B, so that's P, well, we have a smaller, a shallower curve. It's still curved. And then our free body diagram at C, again, gets very, steeply peaked, very similar to what it is at A. And the reason that we're not going to spend a lot of time in this class looking at how so this is our, stress, how to derive these is because in order to determine the actual stress distribution at a cross section, it's an indeterminate problem. You need to understand the deformations of the member and the section at each small little portion of the area in order to determine it. And so for a lot of design applications, that's not practical. You know, there's some good, you know, software which can do it, but for oftentimes that's not appropriate, because when you're doing design, often you have to iterate through multiple different designs or combinations quickly. So you need something which is going to be uh, pretty good. And that's why we use this average stress for axial load. And so the first assumption, you know, assumption for uniform stress is that, you know, we're a slender member. Um, so it's slender member, and section is away from application of load. So what do I mean by slender? So slender is that its width or its thickness is smaller, well, much smaller than its overall length. So how much smaller? The short answer is it depends. But you know, if you are 3-4 times, you're probably just fine. And then the other one is that, you know, the section's away from the application of load. So if you look at free body diagram B, which, you know, we're assuming is somewhere in the middle, you can see, well, there's a little bit of a curve, but it's pretty close to uniform. And if you run the math, this is really how these sections behave, where as soon as you get away from where you're putting the loads on, and you've got, you know, little stress concentrations there, everything kind of just settles out into uniform when we're looking at axial stress. So the second key assumption for when we have uniform stress is that the member is loaded through the centroid. So say we've got our member here, and again a rectangular prismatic section, and we have the load straight through the centroid like that. So you can see where, you know, if that's passing all the way through, it'll land right in the centroid at the section that we have. And you can see where if you've got the, you know, a nice uniform area, well, you're not going to have any internal moment created by the stresses. Now let's compare that to you know, a section that, you know, has a bit of a dog leg in it. So that's our top of our section, and it starts off straight, and then it curves out and around, and then curves back. So we're actually going to load, you know, where we start and end is above and below, but you know, the section that we're interested in will be off to the side here. So we want to look at this section here. And again, we have a force P and a force P. Those are lined up, and the centroid of the section over here is some distance delta away. So if we look at a free body diagram of just this bottom half, you know, we have our section, and it curves around with some distance. We have P, and if we have these elements acting right at the centroid, well, we need both P and a moment M to balance that section. And you got that space D, and that moment M equals P times delta. And so you can see here, because we have the presence of both a moment and a axial force, you're not going to have a uniform force across the section. You're going to have both of these forces acting there. So that's our second or third assumption for uniform stress. So just to sort of summarize assumptions for uniform stress in an axial member. One, that it's a slender member. Two, that the section that we care about is away from the application of load, so section away from application of the load. And three, the force acts through the centroid. Through the centroid of the section of interest. So like I said, if we look at our previous example, yeah, the force was through the centroid at the top here, but at the section of interest, it's definitely not going to be uniform because we've got that presence of the moment. And so if we have all three of these components coming in, then we can use, this average stress sigma equals P over A. And so that's our introduction to axial stress.